All right, welcome to the Explainer. Today, we're diving into something you see literally every day, whether you're taking a pizza out of the oven or just feeling a rock that's been sitting in the sun. We're talking about transient heat conduction. Now, I know that sounds super technical, right? But stick with me, because it's really just the science behind how things heat up and cool down. Let's get into it.
So let's kick things off with a little puzzle, one you've definitely experienced. You pull a big roast out of the oven and the outside is perfectly browned, but the center is still basically raw. And yet, if you take a small, hot copper ball, it cools down almost perfectly evenly all the way through. Why? They're both just objects losing heat, so what's actually going on here? Well, to figure that out, engineers don't just jump into the deep end. They start with the simplest model they possibly can. Think of it like climbing a ladder of complexity, and this is the very first rung. It's called the lumped system. So what is this lumped system? It's a really clever shortcut, actually. It basically pretends that the temperature inside an object is the same everywhere. The whole thing is just one big lump. Now, the temperature of that lump can and does change over time, but at any single moment, every single spot inside that object is at the exact same temperature. One number tells you the whole story. Okay, so let's bring it back to our original mystery, the copper ball versus the roast. For the copper ball, this lumped system idea works perfectly. Copper has a high thermal conductivity, which just means heat zips around inside it so fast that the temperature stays pretty much uniform as it cools. But the roast? Totally different story. It has low conductivity, so heat just crawls from the outside in. That's why you get a hot surface and a cold center, and why our simple lumped model completely falls apart. So how do we know for sure when we can use this shortcut and when we can't? And that's where our next piece of the puzzle comes in. Engineers needed a foolproof way to decide if they could use the easy, lumped method or if they needed something more powerful. And that decision, well, it all comes down to one simple, powerful number. Right, so how do we actually know? When can we get away with treating something complex, like that roast, as if it were a simple copper ball? It turns out the answer is in comparing the two parts of heat's journey into an object. Here's a great way to think about it. Imagine heat is trying to get to an island. First, the heat has to get to the surface. That's a process called convection. Think of it like boats arriving and docking at the island's harbor. Then, once it's there, the heat has to move from the surface into the center of the island. That's conduction. And you can picture that as buses taking the new arrivals from the harbor to the town's inland. And that, right there, is what the Biot number tells us is just a ratio. It compares the traffic jam inside the island, the resistance to conduction, our bus traffic, to the traffic jam at the harbor, the resistance to convection, our boat traffic. If the buses are super fast and the boats arrive slowly, there's no backup at the harbor. But if the boats keep showing up and the buses are slow, you get a huge pileup right on the coastline. And here it is, the magic number, the engineer's secret handshake, a Biot number of 0.1. If you calculate the Biot number for your problem and it's less than or equal to 0.1, it means your internal bus traffic is so fast it's basically irrelevant. The temperature inside is uniform enough, and you can safely use this simple lumped system model. We're talking an error of less than 5%, which for most real-world work is absolutely fantastic. Okay, but what if you're not below that number? What about our poor roast beef? In that case, the buses are slow, the harbor is jammed, and location starts to matter. A lot. Things get more complicated for sure, but don't worry, engineers have some really elegant tricks up their sleeves for this too. Look, the full-blown physics here, it involves some seriously gnarly math. We're talking partial differential equations, the kind of stuff that gives people nightmares. But who wants to do that if they don't have to? Thankfully, just like before, there are some incredible shortcuts that give us great answers without all the mathematical heavy lifting. To use these shortcuts, we need one more tool. Let's introduce another key player, the Fourier number. The easiest way to think about this is as dimensionless time. It's not about seconds or minutes, it's a measure of how far the heat has managed to soak into the object. A small Fourier number means you just put the roast in the oven. A large one means it's been in there for a good long while. Okay, let's see this in action. Imagine a hot wall that we suddenly start to cool from both sides. Right at the start, time is 0, the whole thing is uniformly hot. Okay, a little time passes. See that? The surfaces are cooling down, but the middle? It has no idea anything has even happened yet. Then, a bit later, the cooling effect finally punches through to the center, and its temperature starts to drop. And if you wait long enough, that temperature profile gets flatter and flatter until the whole wall is at the new cool temperature. So, you ready for the big cheat code? The full, exact mathematical solution is this hideous infinite series of terms. It's a nightmare to calculate. But it turns out that for simple shapes, after just a little bit of time passes, all those other complicated terms in the series, they just kind of fade away into nothing. They become so tiny, they don't matter anymore. All you're left with is the very first term. So engineers just use that. It's called the one-term approximation. And it's shockingly accurate, usually less than 2% error. And the best part, all the tricky constants you need are already calculated for you in tables.
All right, we've handled simple lumps. We've handled infinite walls and long cylinders. But the real world isn't made of infinite things, right? So what do we do when we have real objects with real shapes? You got it. Think about a simple can of soup. It's not an infinitely long cylinder, it's a short one. Heat's coming in from the round sides, but also from the flat top and bottom. So now we're in 2D. Does that mean all that work we did on 1D problems was for nothing? No way! This is where it gets really, really cool. The answer is something called, fittingly, the product solution. And the idea is so simple, it's honestly beautiful. It says you can find the temperature solution for a complex 2D or 3D object by just multiplying the simple 1D solutions that make it up. Think about it like this. A short cylinder is really just the intersection of an infinite flat wall and an infinitely long cylinder. So to find the temperature anywhere inside that can of soup, you just calculate the solution for the wall, calculate the solution for the long cylinder, and multiply them together. That's it. It's like you're building the answer out of thermal Lego blocks. You just snap the simple solutions together to build the complex one. It's brilliant. So, let's take a step back. We've just climbed this whole ladder of complexity, from a simple lump to a 3D object. And what we have now is a complete, practical toolkit for solving almost any of these problems. Let's lay it all out. This flowchart basically sums up everything. It's your decision-making guide. First thing you do, always check the Biot number. If it's tiny, less than 0.1, your life is easy. Use the lumped system. If it's bigger, you look at the shape. Is it a simple 1D object like a huge wall or a really long pike? Great, use the one-term approximation. And if it's a more complex 2D or 3D shape, you just build the answer with our Lego block method, the product solution. You know, there's a quote from a famous engineering textbook that says, "The temperature of a body, in general, varies with time as well as position." That's it. That's the whole ballgame. That's the fundamental truth we've been trying to wrestle with. And everything we just talked about, that's the engineer's toolkit for taming that simple reality. And believe me, this isn't just for exams. This is the real-world engineering behind how a steak thaws, how a spacecraft's heat shield works, and even why you have to bury water pipes deep enough in the ground so they don't freeze in the winter. So now that you have this mental toolkit, start looking around you. Where else do these principles pop up?